Okay, after completing the topic of stability, now we are going to discuss the next topic, which is steady state error. We have already discussed about the steady state, that what is the steady state of a system when the transients of a system die out and system reaches up to a steady state. Then this is called as the steady state. And when we apply some particular input for a desired output, and if we are not getting the desired output but it is deviating somehow from the desired value, then we said that there is some error in the steady state. So we have to evaluate that error, that is called the steady state error. So we'll discuss what is the steady state error in detail now. These are the topics we'll cover under the steady state error. First we'll define the steady state error. Then we will discuss the types of feedback systems. These types of feedback systems are actually important for the study of the steady state error, because you will see after completion of this topic that by just evaluating the system type, your work to calculation for to steady state error will be reduced. So your work or your calculation will be reduced to calculate the steady state error if you know what is the type of a particular feedback system. Next we will study the test inputs, how many test inputs we have or we use, and then we will see for different types of input what are the value of the steady state error for different types of inputs and for different types of systems. And we'll also study the error constants to study the magnitude or the value of the steady state error for different types of systems and for different types of inputs. We have some particular value for a particular type of input, and we have some particular value of steady state for some particular type of feedback system. So then finally we will define steady state error for every type of system and for every type of input. Then we will study the gain design, that if we have a particular steady state error specification, then how can we find the value of the gain. And then we will study the steady state error for non-unity feedback systems. We define initially the error constant and steady state error for different type of systems for a unity feedback system, and later on we will discuss steady state error for non-unity feedback systems. And then we will see the steady state error for disturbances, that disturbances actually acts as an input for the system. So it means that if not only one input, we have disturbance also or some other input also in the system, then how we'll calculate the steady state error in that case. So the steady state error is defined as the difference between the input and output for a prescribed test input as time t tends to infinity. Time t tends to infinity means here that after reaching the stable condition of the output, obviously after some settling time, you have discussed settling time in time response specifications. After reaching at some steady state, and after obtaining the stability of the system, the output is actually settled up to some particular value. That value is called the steady state value. After all the transients of the system die out, then we say that the system has a steady state, and at that particular state, the difference between the input and the actual output of a system is called a steady state error. Now we define the types of feedback systems. The general standard form of the transfer function is, in the polynomial form, we write it as gs equals to k with a subscript m1 plus b1s plus b2s. This is a polynomial form. b1 is the coefficient of s and b2 is the coefficient of s square, and so on. bw is the coefficient of s raised to the power w. And the numerator is s raised to the power m, where s is the a pole at origin, or sometimes 1 upon s is called the integrator. So we have s raised to the power m, some m poles at the origin, and the polynomial here is 1 plus a1s plus a2s plus a2s square plus au s raised to the power u. So this is the transfer function in polynomial form, or in the factored form we'll write as g of s equals to km 1 plus t1s, 1 plus t2s, 1 plus t3s, and so on up to the number of zeros we have in the above polynomial, divided by s raised to the power m 1 plus tas plus multiplied by 1 plus tbs into 1 plus tcs, and so on up to the number of poles we have in the polynomial above. This is actually general standard form, and these are actually giving us the poles and zeros of the system. If we see carefully here that the above factors which are actually the making the polynomial of the numerator, we see that these are the zeros, and in the denominator we see that we have some poles. Or if we write it as gs equals to km, the whole transfer function remaining, if we separate the gain we can just tell it as g prime s. In this case the poles at the origin actually tells us about the system. If m equals to 0, that is the transfer function is km upon s raised to the power 0. The remaining poles and zeros are at their own places. Km upon s raised to the power 0, it means that it is system type 0. S raised to the power 0 means there is no pole at origin. If we have m equals to 1, then it means that this is system type 1. System type 1 means here we have 1 upon s. 1 upon s means we have one pole at origin. And m equals to 2 means system type 2. It means we have here 1 upon s square. 1 upon s square indicates that it is system type 2. So by observing the number of poles at the origin, we can easily find the type of the feedback system. If it is 0, the system type 0. If it is 1, system type 1. And if it is 2, we have system type 2. How we formally define system type 0? In system type 0, a constant actuating signal results in a constant value of the controlled variable. In type 1 system, that is m equals to 1, a constant actuating signal results in a constant rate of change of the controlled variable. And if type 2 system, that is m equals to 2, a constant actuating signal results in a constant second derivative of the controlled variable. So if you remember that while we were studying the transfer function of the DC motor, while we were discussing the transfer function of the DC motor in the block diagram part of the course, we have discussed that either we take displacement or the velocity as the output. So for the same input, that is the same constant actuating signal, either we are taking it out velocity at output, or we were taking the displacement or position at the output. So and remember that at that point we have added an integrator 1 upon s when we consider the displacement or position as the output, and we did not include that integrator when we have velocity at that output. So we have include actually one integrator, that is 1 upon s in the block diagram. So here for type 0 system, the constant actuating signal results in a constant value of the control variable, and for the same constant actuating signal, if we have system type 1, it means that we will get the controlled variable or the output as a constant rate of change. So that is, for example, if we have velocity at the output. And for system type 2, a constant actuating signal results a constant derivative of the controlled variable. ramp function actually has the ability to test the system, how the system would respond to a signal that is actually changes linearly with the time. And for example, if the input variable represents the angular displacement of a shaft, then the ramp input denotes the constant speed rotation of the shaft. So this is how we define the system type, that by observing the number of poles at origin, we see that what is the system type. Now we define formally the steady state error by using some equations. The transfer function between the error signal and the input is E upon R, or the error ratio. This is equal to 1 upon 1 plus GS. If you have remembered that while we were discussing the block diagram, we say that this error or actuating signal or error signal is equals to the difference of R minus this feedback signal, that is equals to R minus B, where this feedback signal B will be equals to the feedback transfer function multiplied by CS. Here for the unity feedback systems, we are actually considering H of S or the feedback transfer function equal to 1. So here E equals to R minus B. If you have remembered, we have discussed in detail this derivation, and B equals to HC, and then we put the value of this B in E equals to R minus B, and we have obtained this expression E upon R, that is equals to 1 upon 1 plus GS. Obviously at that time we have derived for the canonical form, and that was like E upon R equals to 1 upon 1 plus GH, but here because H is considered as 1 or for unity feedback system, so we have defined here E upon R equals to 1 upon 1 plus GS. And if we find the value of E of S, then we will just multiply this R of S at the right hand side of the equation. So we'll get E of S equals to R of S upon 1 plus G of S. E of S is actually error in the S domain, and if we discuss in the time domain, we see that this is E of T. This E of T is actually the difference between the input signal and the output signal. So this is marked as equation number 1. E of S, that is error in the time in the S domain, equals to R of S upon 1 plus G of S. Now the steady state error is actually defined. We have discussed that in the time domain, the actual value of the output at a steady state. So actually ideally we say that we obtain this value at time infinity. So we say that at time t tends to infinity, E of t is actually E defined as the steady state error. E of infinity is defined actually as the steady state error. If you have remembered, you have studied the final value theorem in the Laplace transform chapter when you were studying the property or the theorems of the Laplace transform, that in the time domain, if t tends to infinity E of t, then in the S domain it will be equals to limit S tends to 0 S times E of S. This is what the final value theorem implies, that limit t tends to infinity E of t equals to limit S tends to 0 S times E of S. We have some limitations when we apply the final value theorem, that S times E of S should not have any poles on the j omega axis or in the right half of the S plane, that is the system is stable. Obviously we have to calculate the steady state error only in the case when the system is stable. If we found that the system is unstable, there is no use of the steady state error, because we are actually not getting any steady state. The system is unstable. So obviously the condition of stability should meet while we applying the final value theorem, and this is the limitation, that S times E of S value should not have any poles on the j omega axis when we apply the final value theorem. So when we apply the final value theorem, we put the value of E of S from equation number 1. We have in the last slide discussed. So E of S, when we put the value of E of S, we have S times E of S, or S is the multiple and E of S is R of S upon 1 plus G of S. So steady state error actually become in the S domain as limit S tends to 0 S times R of S upon 1 plus G of S, and we have marked this as equation A. In this equation, if you have remembered what is R of S, R of S is the reference signal input, G of S is the forward path transfer function. So we will put some different values of input, reference input R of S as unit step function or simply step function or ramp function or parabolic function in this expression, and then we'll see that what will be the value of a steady state error for different types of inputs. Similarly, when we put the value of G of S, that is G of S is different for different types of feedback system. It is type 0, type 1, type 2. So we'll put the value of G of S here, and then we will see when we has no pole at the origin, that is 1 upon S to the power 0, then what will be the value of a steady state error for a step function. Then we see that when we have 1 upon S in the as integrator in the transfer function for the step function, then what will be the value of the step error constant in case of type 1 and type 2 and so on. We'll change the value of system type here in this part of the equation, and we'll change the system type here in this part of the equation. So we'll change the value of R of S for different types of inputs, and we'll change the value of G of S for different types of feedback control systems, and ultimately we will have some combinations of the values of the steady state error for different types of systems and for different types of inputs. These are different type of test inputs. These are actually input signals, or sometimes we actually represent some practical input signals by these signals. For example, for a DC voltage, we represent a step function as an input. So these are also called some test inputs. So the test inputs are step function, ramp function, and parabolic function. So we have obviously we can have more higher order system, higher order inputs, but usually at higher order inputs above parabolic function, we have not stable systems, and we sometimes found jerks in the system. So we not prefer use higher order inputs other than the parabolic. Maximum we use the parabolic, otherwise usually we use step function and ramp functions. These are the test waveforms we'll use for the steady state error. Here this is the step function, and in the time domain it is 1. If it is unit step function, its magnitude is 1, otherwise it may have some magnitude, and its Laplace transform is 1 upon S in the S domain. This is the constant function, linearly increasing. This is t raised to the power 1. It has constant velocity, it has constant position, it's a constant rate of change here in this ramp function, and in the S domain we represent it by 1 upon S square. This is the parabolic function, and it represents a constant acceleration, and mathematically in the time domain it is represented by half of t square, and in the S domain we represent it as 1 upon S cube. Obviously this magnitude of these input functions may change, but here this half is actually just put for the mathematical convenience, that if you observe the table of the Laplace transform, that we have simple 1 upon S cube for 1 upon 2 t square. So these are the test waveforms with corresponding time and S domain functions. If we define steady state error for a step function, then this is actually the input. This is straight line step function is the input, and if this is the output 1 and this is the output 2, this is the actual output we want, if we the exact output, and if we are not getting this output, whether we are getting this output, then this will be called the steady state error for the step function input. I hope you have remembered that when we were discussing the time domain specification, we see that the output value of the output or the magnitude of the output is actually acceptable in some particular range, that is 2% to 5% of the final value. So we need to check that whether the steady state comes between that range, that it should be false between plus minus 2 to plus minus 5% of the final value. Then the corresponding difference is called the steady state error for step function input. This is for the ramp function input, that ideally if this is the input, if we have multiple outputs, so the difference between the input and the some output is called the steady state error. Obviously when this system has a constant output value, if we increase this line here, if we increase this line here, then we see that this is the constant value, or the system becomes stable. After that point, that we say that this is time t tends to infinity, then at this point this is called the steady state error. This is the steady state error for the parabolic function, that this is the parabolic function input r of t, or the reference input, and this is if we are getting this output, then after reaching up to the steady state, or system reaches up to a stable state, then the difference in these two is called the steady state error for parabolic function input. So this is how we define the steady state error for step, ramp and parabolic function pictorially. Now we will drive the value of the steady state error for step function input. So the first is static position error constant Kp, and steady state error for step input. So we define step input as Ru of t. The reference input is Ru of t. R is actually the magnitude. For a unit step, we'll consider is just u of t, and it's when we take the Laplace transform in the S domain, the corresponding value is R upon S. Obviously, if we are considering it as u of t, it will be 1 upon S for unit step function. In some books, you'll find that they have derived these expression in the form of unit step function or unit ramp function, or in some books it is defined as with a constant magnitude R. So we can define in both way. So here we have defined reference input as R of t equals to Ru of t, and the corresponding value in the S domain is R upon S. Then equation A we have previously defined implies that we have put actually the value of R of S here, S times R of S. So R of S is actually R upon S upon 1 plus GS. If you have remembered, we have derived the equation A, S R of S upon 1 plus GS. So R upon S, S and S will be cancelled out here. If this S is cancelled by this S, then it will become R upon 1 plus G of 0. Please remember that this R is actually a constant value, that is the magnitude of this input function. For example, if this is 10 u of t, then this 10 is actually the magnitude, and when we write S R of S in the bracket S, it means that R is a function of S in the S domain. So if we apply the limit S tends to 0, this is actually a constant value R, so we don't need to put we don't need to apply the limit. We apply the limit here in the function in G of S, because this is a function of S. So R upon 1 plus G of 0. We define this G of 0 or G of S as position error constant. Kp equals to limit S tends to 0 G of S. This defined as step error coefficient, or sometimes called step error constants. And if we put the value of here as Kp, then it will become E of Ss equals to R upon 1 plus limit S tends to 0 G of S or Kp. So it is steady state error for step function is defined as R upon 1 plus Kp. Now if we define this steady state error for different types of systems, so we know that for type 0 system we have m equals to 0. So if m equals to 0, it is km upon s raised to the power 0 is 1. So k upon 1. We have also put a 1 here. So k upon 1. These all factors which are actually multiplying in the numerator and denominator will be equal to 1, because each factor will be equal to 1 if we apply the limit. For example, in 1 plus t1s, is s is 0, the second term will become 0 and it will become 1 plus 0 equals to 1. Similarly, in this factor, if we apply the limit at s is 0, then 1 plus 0 is 0, so it will become 1. So all these factors will become 1, and we take the product of all these factors, it will become again 1 into 1 into 1 and 1, and similarly here in the denominator it is 1 into 1 and 1. So this is actually equals to k. So for system type 0, Kp is defined as k. For system type 1, this is actually s raised to the power 1. If m is 1 for system type 1, this is actually k upon s raised to the power 1 or k upon s, and when we apply limit, k upon 0 will become infinity. So it means that the system type, for system type 1 it will become infinity. Similarly for higher order, if we put s equals to m equals to 2, it is k upon s square, and if we apply limit, it is k upon 0 will become infinity. So for type 1 or higher order systems, the value of static position error constant is always infinity. It is k for type 0 system. So we can define for type 0 system, steady state error will be equals to r upon 1 plus kp. For this formula, it is actually specific for a step function input, because we have written here kp, and for type 0, because we know that step error is actually infinity for other types of inputs, or other types of control systems, type of control system, that is for m equals to 1 and greater. So if we have infinity here, then r upon 1 plus infinity will be r upon infinity, and that will be equal to 0 for type 1 or higher order system. The general expression is r upon 1 plus kp. When kp is infinity, r upon infinity is 0. So we can say that for type 1 or higher order system, actually the value of steady state error will be 0. So obviously it is very good if you have a steady state error equals to 0. So we can desire a 0 steady state error if we have a type 1 system and step function as an input, then we'll get a 0 steady state error. Now we define the steady state error for type 0 system with the step function in summary as r upon 1 plus kp for type 0 and 0 for type 1 or higher order systems. We can see here for that when we have a step function input, this is the output, and this is reference signal input, this is C0 is the output, and actually the difference in these two is called the steady state error. Sometimes we not represented by k0 also, kp represented by k0 also. Now we'll define the steady state error for ramp function input. For ramp function, we know that r of t equals to r t u of t. Again, this capital R is actually the magnitude, and when we take the Laplace transform, r of s will be equals to r upon s square. When we put the value of this r of s in equation A, we define it as steady state error for ramp function. We put the value limit s tends to 0 s r of s, we put r upon s square. We put r upon s square in place of r of s. Then the 1 power of s will be cancelled here, and we'll get r upon s 1 plus gs. And when we put this s in the denominator, it will be simplified as r upon s gs, because when this s will be in the denominator here, it will multiply by s, and when we apply limit 0, it will become 0. So this term will become 0, and this term will become s times g of s. Then we define the ramp error coefficient E of a steady state equals to R upon KV, when the KV is defined as limit s tends to 0 s g of s. So this value is actually defined as KV or ramp error coefficient, and then the steady state error will become R upon KV. Now we define the ramp error coefficients first for type 0 system. For type 0 system, here we have s raised to the power 0 in the denominator. S raised to the power 0 is 1. So actually we have s g of s. So this s, this is g of s. So when we apply limit s tends to 0, this s will become 0. So the overall value of the ramp error coefficient will be 0. And now for type 1 system, if we have s times g of s, and when m equals to 1, this is k upon s, then this s will be cancelled by this s as m equals to 1, and effectively we have k. So we say k1 or simply k, as we have discussed that all these factors will become 1. 1 plus t1s will be 1 when we apply limit, 1 plus t2s will be 1 when we apply limit, and so on. These all factors will become 1, and the product of 1 is always 1. So we have k as the final value of the ramp error coefficient for system type 1. And when we put m equals to 2 for type 2 system or any other higher order system, we put the value of m greater than 2. So for this time we have s square here. Let's say if we have s square here, then we cancel it. Then we cancel it. Minimum it is s square. Then obviously at least one power of s will be here. So when we apply limit, then it will s raised to the power 0 k upon s, and when we apply limit this will become k upon 0 and the result will become infinity. So ramp error coefficient in case of type 2 or higher order system will become infinity. Now we put the value of these ramp error coefficients in the steady state error. Then we say that R upon kV, then kV is actually 0 for type 0 system, then R upon 0 will be infinity. So this is actually not a desirable case when we have steady state error infinity. We don't need so much steady state error. So this is a very huge or large value of the steady state error. And when we put the value of k equals to k in type 1 system, the steady state error will become R upon kV, and it is actually some limited value for type 1 system. And similarly for type 2 system, when we put the value of kV as infinity, then R upon kV or R upon infinity will become 0. So actually we have a 0 steady state error for type 2 or even higher order systems. So this is actually a good thing that we have a steady state error 0. So in this case, for ramp function for type 0 system, the value of the ramp error coefficient is 0. For type 1 system it is k, and for type 2 system it is infinity, and the corresponding steady state error is infinity for type 0 system, and R upon k for type 1 system, and 0 for type 2 or higher order systems. Now similarly we have summarized the steady state error for the ramp function ramp function input as infinity, R upon kV, and 0 for system type 0, 1 and 2 respectively. Now we define the steady state error for parabolic function, and again we have used the same method, that this time the function is defined at R upon 2 t square u of t, and when we take the Laplace transform in the s domain, it will become R of s equals to R upon s cube. Similarly, we have put the value of R of s in equation A in the similar fashion we have done for ramp and step function, and this time after cancelling one power it will become R upon s square, and when we move this s square in the denominator and we apply limit, then this term will become 0 and it will become R upon s square g of s. So we define step error constant as limit s tends to 0 s square gs, and the corresponding steady state error will be defined as R upon ka. So this is actually very much similar to the previous two derivations. We have just put the value of R of s in the expression of a steady state error. Now we define it for system type 0, 1, 2 and higher order system. It is very much similar we have done previously for the ramp and step function. So we can see directly here that when we apply the value of m equals to 0, 1, 2 in limit s tends to 0 s square g of s, the value of k is s square g of s. So this is actually when we put the value of m and we apply the limit, we'll get that ka is 0 for type 0 and 1 system, and it is actually k for type 2 system, and its value is infinity for type 3 or higher order system. So we define steady state error for different types of systems by putting the value of error constants. So steady state error is R upon ka for type 0 and 1 system. This is R upon ka or sometimes R upon k for type 2 system, and this is actually 0 for type 3 system when we put the value of ka as infinity in this value. We can summarize as R upon k infinity steady state error infinity for type 0 and 1 system. It is equal to R upon k for type 2 system, and it is actually 0 for type 3 or higher order systems. This is the summary of the error constants. The value of error constant is actually k naught for system type 0, and it is 0 for higher orders for ramp and parabolic error constant, and its value is infinity for higher order systems. So we can see here that for higher order systems the value of Kp is infinity, and the value of system type 0, the value of step error constant is Kp, and the remaining values of ramp error and parabolic error constant is 0. These error constant actually has the ability to eliminate the steady state error. Error constants actually indicates the steady state performance, and generally it is desirable to increase the error constant while maintaining the transient response within the acceptable range so that the steady state error will be reduced. So this is a summary of the steady state error constants, steady state error and error constants for different types of system and different types of input. Here we can note that by increasing the type of the system, we can increase the type of the system by adding an integrator or integrators to the feed forward path. But sometimes it may have some stability problem, and but the design normally satisfactory work if we have 2 integrator maximum in the forward path. Generally higher than that is not desirable or feasible. Now we'll evaluate the error constants. For example, we have a system with the transfer function 500 s plus 2 s plus 5 s plus 6 upon s plus 8 s plus 10 and s plus 12, and we have this forward path transfer function g of s. Then when we apply limit here, because this is a s in the denominator, when we apply limit k upon 0 will become infinity. So Kp is equals to limit s tends to 0 g of g is infinity. Similarly, when we apply limit by putting the value of g of s in s g of s, we'll get the value 31.25, and Ka is equals to limit s tends to 0 s squared g of s. We'll put the value of g of s and we'll apply limit, then we'll see that the value is 0. For step input, the expression for steady state error is 1 upon 1 plus Kp. As the Kp is infinity, therefore the value of a steady state error is 0, because 1 upon infinity is 0. For ramp function it is 1 upon Kv or 1 upon 32.5. That is, for ramp input the steady state error has a very smaller value, 0.032, but it has some steady state error obviously. For parabolic input it is equals to 1 upon k, and because parabolic error constant is 0, so 1 upon 0 is actually infinity. So we have infinite steady state error in case of the parabolic input. This is actually type 1 system. So we see that here we have steady state error for input function input 0 and for parabolic infinity, and we have only magnitude in the case of ramp input because of the system type 1. We have derived these values of the steady state errors. We can also define error coefficients as the ratio of steady state value of the output to the steady state value of the actuating signal for the step function input. Similarly, we can define steady state ramp error coefficient as the ratio of steady state value of the derivative of the output because of the ramp function input to the steady state actuating signal E of t, and similarly we can define parabolic error constant in the same fashion. What information actually contained in the error constants? For example, if we say that a system has kV equals to 1000, kV equals to 1000, we have just done a question in which we have only the value of kV, whereas the value of kp and ka were 0 and infinity. So this is quite obvious from the value of the error constant, as because this is the ramp error constant, simply because there is some steady state error value, it means that first we know that system is stable. Because if system is unstable, we will not have any error value. Second, because we have a value of kV, it means there is no value of kp and ka, and system type is 1. So we can say that system is stable, system is of type 1, because only type 1 system have kV value. Similarly, we have a ramp function as an input because we have kV, so we can say that ramp function is using as an input here because of the finite constant value of the kV. And also we can say that we have some finite value of the steady state error because of the finite value of the kV, and obviously the steady state error between the input, that is the ramp input, and the output is 1 upon kV per unit of the input slope. So these information we may obtained from just a single value of the kV equals to 1000. We can have so much information by just a value kV equals to 1000. Similarly, if we have Kp equals to 1000, we can say that system type 0, we have a step function input and the steady state value is 1 upon 1 plus Kp. In the similar fashion, we can analyze with the value of a step error coefficient also. Now we'll see some examples how we'll calculate the value of error constant and the steady state error. This is actually the value we have already calculated using these values in the previous example. This is another example. We have a forward transfer function and we have Kp equals to limit s tends to 0 g of s. We have just put the value of g of s, apply limit, and we have get the value 5.208. Kv and Ka, both values are 0, and we have calculated the steady state error for step, ramp and parabolic function, which comes as infinity both for ramp and parabolic input, and it has a value of 0.161 for step function input. Now again one more example. This is actually type 1 system. Previously we have discussed type 0 system. In type 1 system we have actually kV. This is 31.25 we have discussed. Kp and Ka does not have any finite value. K is 0, Kp is infinity, and the step error, the steady state error in this case for step function is 0, and for ramp function it is 0.03t and infinity. And now for a second type, type 2 system, we have s square in the integrator. In this case we can see easily that Kp is infinity. When we apply limit, Kv is also infinity, but we have a finite magnitude of the parabolic error constant Ka when we apply the limit in limit s tends to 0 s square g of s. So we have a finite value of 875 in this case for Ka, whereas Kp and Kv both are infinity in this case because we have a type 2 system. And similarly we have calculated the value of the steady state errors, so it is 0 for both for step and ramp function, and it has some very minor value in as steady state error for the parabolic function input. So we have actually discussed both three cases, type 0, type 1 and type 2. We have seen the example of each case. Now in this example we can see that if we have some particular value of the inputs, that is we apply 5 u of t. This is actually a step function with a magnitude of 5, then 5t u of t. This is actually a ramp function with a slope 5, and then the parabolic function 5t square u of t. Then in this case we have just put the values in the same formula, but we have put the value of r as the magnitude 5 here, and then we have calculated the value, and we have seen that we have the value for steady state error value for only for step function, and the remaining two values are here infinity. So it is just an example. If we have some magnitude in the inputs, so how we will put the values of these magnitudes in the formula. If we remember this chart, which is very easy to remember, then we can easily minimize our calculations. It is very easy. It is just the value is 0 below the value of the constants and infinity above the constant. So if we remember this chart, it is very easy. to reduce our calculations. Just remember this table. We don't need to calculate this value of 0 and this value of infinity. We have just calculate the value of in steady state error for ramp function. If we have just remember the values, that we have a 0 steady state error for a step function, and we have an infinity step function, steady state error value for type 1 system. So it is a trick. If you want to remember, you can remember that when we have 0 and infinity values. Now it is the same table. Here in this example, we have to find the value of k, so that there is a 10% error in the steady state. We have remembered that for S it is type 1 system. We just recall that it is type 0 system if this is the power of S, that is n equals to 0, it is 1 for type 1 and so on. We have discussed in many times previously. So here we note that it is system type 1. So we have to find the value of k if we need maximum 10% error in the steady state error. So it means that the value of the steady state error is 0.1. 10% means 0.1. And we know that because there is a system type 1, we only have steady state error in case of the ramp function, that is kv. So we have just put the value of steady state error equals to 0.1, and the formula will be 1 upon kv. So we can find easily the value of kv here. So we have put the value of steady state error equals to 10 here, that is 1 upon kv. 1 upon 0.1 is 10, and we have calculated and simplified, then we'll get the value of k equals to 672. Now we define the steady state error for non-unity feedback systems. If we have a non-unity feedback system, we will simplify our system to a unity feedback system. So here we see that here we have g of s as the forward path transfer function. We have one feedback loop h of s, another feedback loop with -1, and here we have a symbol direct -1 feedback. So here, because we have simplified this whole block diagram, we have this g of s upon h of s minus g of s h of s. It is actually combined, and then this is coming from here, so this is minus g of s. It is actually a derivation, long derivation. You can see in the Norman Nice if you want to see the detailed derivation. Otherwise we just simplify this as g of s upon 1 plus gs hs minus g of s. So this is actually the method how we simplified this type of non-unity feedback systems. So if we want to calculate the steady state error, and we want to calculate the system type error constant, then we'll apply this method. So this is a problem: find the system type error constant and the steady state error for a unit step input. Then we have simplified using this method, and the formula is g of s upon 1 plus gs hs minus gs, and when we put the value of this gh, then we'll get this expression 100 into s plus 5 upon s cube plus 15s square minus 50s minus 400. And if I solve this cubic equation, we'll see that it does not have any pole at the origin. It has 3 poles, one at 3.36, another one as minus 17.69, minus 0.6709. So this is actually does not have any pole at the origin, so we can say that this is system type 0. And now, because this is system type 0, we only have to calculate kp. The formula is kp equals to limit s tends to 0 g of s, and we have put the value of g of s here, and we'll get the value minus 5 upon 4, and we put the value of this error constant in the steady state error, and we have found the value of the steady state error as minus 4. Now we'll see how to calculate a steady state error if we have any disturbance in our system. In case of the disturbance, it is like an input such that we may have more than one input. So here you can see that with the reference signal R of S, we also have a disturbance D of S here. So if we write expression for C of S, we have already done it when we were doing block diagram, that C of S is actually a combination of the signals coming from this side. So it is actually the product of G2 of S cascaded with these two blocks. So this is actually this block is coming from here, E of S multiplied by G1S plus D of S, and the whole thing is cascaded with this G2S or the plant block. And we also note that here E of S equals to R of S minus C of S, which we can write it as C of S equals to R of S minus E of S. Then we equate these two equations and we get an expression for E of S. This E of S actually has two terms. The first is the error due to the reference signal, and the second error is due to the disturbance input. So this time if we have two inputs, it means that we have a steady state error because of the two factors, one for the reference input and another for the disturbance. So we can calculate both separately, and we can just simply add it, as here the inputs are also adding. It is also a general rule that if we have more than one inputs, and if these inputs are adding or subtracting, the output result will also be adding or subtracting in the same manner. For example, we have applied input 5u of t, and we have applied separately 5t square u of t, and if we are applying both inputs as a combination 5t u of t plus 5t square u of t, then the output the error will be superimposed in the same manner as 5 times because of the step response, and 5 plus 5 times due to the ramp function t square u of t is parabolic function. So here also we have actually adding the two steady state error value due to the reference input and due to the disturbance input. So we'll see how we'll do a problem. Find the steady state error component due to a step disturbance. So we have applied the formula we have just derived, and here it is comes out the value as minus 0.001. So we can find the value of the steady state error due to the disturbance. Also we can find because of the reference signal the value of the steady state error, and then we can add it if we want to find the total steady state error of the system. So this is how we have calculated the steady state error for unity feedback systems, for non-unity feedback systems, and for the disturbances. In next week we'll inshallah start the new topic, that is the root locus.